My wife and I get together with some friends from church about every other week, and one of them had a birthday. So we called his wife and said, "What does he like? What kind of thing does he like to eat?" And she said, "Well, he likes sugar cookies." And so my wife, not having made sugar cookies before, pulled out our iPad, which we named Squirt. It's our little Squirt. So we pulled out Squirt and type in sugar cookie recipe, and we found this recipe. 5,489 people rate it 4.5 stars out of 5. I mean, this sugar. I'm like, okay, yeah, do that. Can't go wrong, right? So we make it, and she was like, well, why don't you try one before we take them tonight? And so I did, and I kind of looked at her and I was like, she's like, well, what do you think? And I said, you got to try and put it gently. And I just couldn't. I said, this is the worst sugar cookie I've ever eaten in my life. And I said, but it's not that bad. And she's like, what does that mean? I said, I've never had a sugar cookie worse than this, but it's not that bad. So I think it'll be okay. So we take it there, and I of course get in front of all my friends. I'm like, okay, we brought these, happy birthday, but total disclaimer. So a couple of them try it, and they're like, yeah, they're just not good. And so we come home, and my wife is like, I don't get it. I was like, 5,489 people can't be wrong. What's the deal? And so she opens the recipe again, and she looks, and she goes, I I totally forgot to add the sugar. And I said, you made sugar cookies with no sugar? And she said, I rolled them, and I forgot the cup of sugar that goes in there. I was like, So anyway, this was just last week. So last night, actually, she brought a whole new batch and totally redeemed herself. We kind of set it all up anyway, it was fun. So my point in all that is we've made it through CVOICE. Essentially Cisco Voice, how to set up voice gateways as a whole, and now we're into the missing ingredient, which is up till now the course is 5,489 ratings. This has been great. We get voice gateways. I've got SIP. I've got blah, 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 but it just tastes like the worst sugar cookies you've ever had in your life if you don't have this, and that is quality of service. It's the missing sugar. So quality of service, I'm sure you've heard at some point what quality of service is all about. So I want to specifically address who are the evil villains in the network. What does quality of service fight against? We'll look at some of the tools to manage QoS, and then at the end of this, it'll be a couple nuggets on quality of service. We'll look at the modular QoS CLI, which is essentially how Cisco does quality of service. I thought this sugar cookie incident happening this week was so appropriate, just because I've seen it go down. I've been at voice over IP deployments where there were no quality of service, and it gets really ugly really quick. And you have to remember, you and I, when we look at these phones, I'm looking at an IP phone on my desk, a 7970. It's beautiful. I'm looking at it, I'm like, okay, this is cool, because I know what's going on behind the scenes. I know codecs, voice VLANs, ITSPs, I know dial peers, and how this phone gets to where it's going. I'm like, this is revolutionary when I look at it. You know what an end user sees when they look at this? you know it. It's a phone. That it's big, it's glossy, and they're like, well, it's a pretty phone, but it's a phone, and they pick it up and they call their mom. And if they're talking to their mom and it's, Mom, I'm sorry, say it again. Hello? If you can hear me, I'll call you on my cell. Click, slam, the receiver goes down. It only takes a day of calls like that before their opinion of this beautiful voice over IP system is, it's like my sugar cookies. It's the worst sugar cookie I've ever had in my life. This is the worst phone system I've ever had before, and it gets real. I've talked to people where it's like buying a computer that just keeps crashing, and they don't help you, and tech support fails, and all that kind of stuff. It's like I've talked to people where I suggest, I'm like, yeah, maybe voice over IP, you should go that way, and they immediately, no way, I will not touch that with a 10-foot pole. And I'm like, oh, you've been to a voice over IP network that has had no quality of service. So here's what we're fighting. Quality of service is meant to take out these four evil villains. Think of quality of service as like some kind of superhero, but this is kryptonite. Quality of service is not meant to address a lack of bandwidth. Meaning, You got a T1 line maybe as your uplink to some carrier, and the data traffic is just saturating that. Now with quality of service, really, let me quality of service is a huge topic. We can dive into a lot of depth with it, but if you really want to boil it down and say what is quality of service, it just says, okay, we've got 5 packets in a line. There's only enough bandwidth to send 4 of them, and 3 of them are web surfing. So how about I take this one and move it to the front of the line and send it? That's really all quality of service is. It's packet discrimination. It's a way of looking at packets and say, you are more important than you, so you will go first. That's the end of the story. Now, if this thing is saturated all the time, let's say it's a T1 line, it's just always maxed out, quality of service will be able to squish the bandwidth down for the data and allow the voice to start getting through. But if you squish it down, I mean, your data is already choking. You're going to start ending up with your data network, the whole foundation of everything, not working because you've got this lack of bandwidth. I always think of this like the Titanic. If you've got a lack of bandwidth, your ship is sinking, and all you can do is rearrange the deck chairs of which deck chair hits the water first. Now, these 3 quality of service can help with. So first off is delay. Delay is how long it takes a packet to get from the source to the destination. Now, it's not something we're used to in the data world. We don't usually care about delay. I mean, I'm copying a file using FTP from one site to another. I don't care that it's a 200 millisecond delay. I really just care about the bandwidth between those 2 sites to make sure that I can get that file through. However, on the voice side, it's all real time. We're communicating, we're talking. It is time sensitive. Like I have to hear back from them in a certain amount of time, or it just becomes unnatural. You've all seen the news before. When somebody is overseas, the newscaster's like, so John, what's it like in the war zone in whatever country you're in? And John is staring blankly at the screen, silent. Oh man, it's scary. There's bombs. I mean, you get these weird, awkward delays, which we've now categorized as normal because we know, there's like satellite delays and whatever else getting there. Well, on a phone call, that doesn't work. I mean, if you can't see the person standing there with their hand to their ear microphone, staring blankly, you're trying to talk and you're like, hello, and then they get it delayed and they're, oh, what, huh? And you just start talking over each other. It's a very unnatural phone call. So delay is definitely an evil villain that we want to prevent. Now, some delay can't be prevented. It takes electricity. It takes packets, it takes data, a certain amount of time to travel distance. It's the speed of light, and it's really fast. But I mean, when you have, one side of the world talking to another side of the world, it's going to take some time to travel around the world. That kind of stuff you can't help. However, you can help what's considered the variable delays. Like if somebody's standing in line and there's other packets ahead of it, well, I'm going to say, I don't want to wait for those packets. I want to move him to the front of the line so that we don't have this delay. So as a Cisco technician, we focus on taking out the delays that we can handle, the variable delays, and the fixed delays, the things that are unmovable, like the speed of light, we can't change that. We just let those be. Now we come down to jitter. Jitter is delay variation. That's another word for jitter. What that means is, let's say we've got an IP phone over here and an IP phone over here, and so you're talking and it's sending hundreds of packets, all the time, just spewing them out. And so one packet goes across the T1 line and reaches his phone, and end-to-end delay on that was 100 milliseconds. It took it that long to get there. And then the next packet goes out, and then it took it 120 milliseconds. And the third packet came out, and it took it 80 milliseconds. So we have this kind of, non-steady delay, if you will. So this would be considered 20 milliseconds of jitter. This would be considered 40 milliseconds of jitter. Delay variation. Maybe the fourth packet shoots up to 150 milliseconds, which is 70. I got to stick with simple numbers that I can do math on. 70 milliseconds of delay variation, and that's not good. When we're dealing with voice, we need to have it smooth. If you think about how you're hearing, like think about me talking to you right now, it's a smooth play out. You're hearing my voice in a smooth way. There's no delays between it. So since you can't just say, okay, well, here's a packet, that's the sound eh, and then wait a little while. Here's another packet, that's the sound ooh, and putting it together that way. No. Inside of here, they have what's called a dejitter buffer, or it could be inside the phone, depending on what device is handling it. But we'll look at the gateway itself. A de-jitter buffer takes the packets that are coming in and holds them to where it can let everything catch up. Think of it this way. When CD players first came out, remember when they had portable CD players? I had one of these that you would get from the store, and you would have your CD in there, and you couldn't bump them. Because it's, the CD is a spinning object, and if you bump them, the laser can't read it, and the song skips. I remember trying to mow the lawn with this big old fat CD player strapped to my side, and I'm trying to like limp, if you will, with one foot so it won't make the CD skip. And then Sony came out with a CD player that had ESP. It's amazing. I remember this extended skip protection, where it would actually read ahead on the CD 60 seconds, so you're actually hearing the song that it read on the CD using later 60 seconds ago or 30 seconds ago or whatever the value was. So you could shake that CD player for 30 seconds and you would never hear it skip until it reached the end of its buffer. Well, the de-jitter buffer is the same thing, but it's not, obviously, you can't delay your phone call 60 seconds. It's a dynamic, the router tries to figure it's dynamic, it makes it larger or smaller, but it's in the millisecond range. And if what it's trying to do is catch all the packets so it can get a nice smooth play out for this and kind of bottle them up. So really a de-jitter buffer, you can think of it like a read ahead. Like on the CD, it's kind of reading ahead of the conversation. But, that's weird. If you think about it, it's like, how do you read ahead of a phone call? Well, what you do is you delay it just enough for the packets to catch up so it can get a nice smooth play out. So when you have these big gaps like this, these big jitters, big differences in delay, the de-jitter buffer can't adjust to big swings like that. So what happens is it says, okay, well, I'm queuing these up, and oh, well, it looks like I've passed, we'll say 20 milliseconds or 30 milliseconds, this packet must not have arrived. So if it does arrive, 70 milliseconds later, it's going to get dropped. So that ends up being clips in the conversation and glitches. So jitter, that's one of the things that we want to make sure of, is not only do we have control over our delay, but that it's a consistent delay. If we have a delay of 100 milliseconds, that's fine. Let's just make sure all the packets get that delay of 100 milliseconds. And the last one, of course, is I'll say the worst of all, if you will, but packet loss. Packet loss is where you lose data from your stream, whether it be bad packets, whether it be things like this where it drops them because they were too delayed. That will immediately impact the voice conversation. Now, the DSPs will try to hide it. It actually has packet loss concealment. Matter of fact, if you look over here, you see a loss of less than 1%. Cisco says, we want to meet the standard of losing less than 1% of packets, which sounds like, oh, that's not much. But if you think, a phone call is sending hundreds of packets every few seconds. So it's like, well, I dropped a packet every second or two. And Cisco says, I'm okay with that, because the DSPs inside of these devices do packet concealment, packet loss concealment. So if they detect that a packet has been lost, it will fill in the sound. It'll actually bridge the sound from the previous packet to the next. It's if you start losing too many packets that sounds bad. That's where, and I think I mentioned this earlier in the series, where you start sounding like a robot because it's dragging out sounds way too long, and you start, I am an electronic person, because you don't get that normal human voice changes in there. So loss is definitely something we want to prevent. So this is the standard to meet. On the right side, we see our one-way delay is 150 to 200 milliseconds at most. You go beyond that and you start getting those unnatural, TV broadcaster style conversations when they're overseas. Jitter, we need to have less than 30 milliseconds of jitter. So again, we've got a packet come across, it take 100 milliseconds to get there. The next one shouldn't be any more than 130 milliseconds delay at most. We don't want it to be there. And then last thing is, with the bandwidth, when we're doing our bandwidth calculations, you need to look at the codec. Your phone calls can take from 21 kilobits per second. If you're using like that G729 with the header information in there, about 21 kilobits per second, all the way to 320 kilobits per second, or more. When you get into the wideband or video or things like that. So you really have to know how much bandwidth this is going to require. Okay, let's look at the tools we have at our disposal. This is, think of this like the suite of quality of service. So this is like your tool belt with all these individual tools sitting inside of it. The first kind of quality of service tools we have is classification. And classification tools are able to separate and identify what the different traffic types are. So, for instance, a typical classification tool would be an access list, to where I could say, okay, if I'm matching these source addresses or this range of ports, I'm going to say, as I've got my router and all the traffic is coming in, I'm separating them using an access list and saying, this type of traffic, you go stand over there. This type of traffic, you go stand over there. Without this, we can't tell the difference. So some classification tools would be like an access list. You could use an incoming interface, like if it comes in on the VLAN 5 interface or fast Ethernet 0/0.10 or something like that. You could classify it using that. You can classify it using tags, which is actually what we're going to talk about next, and those marking tools. There's many different ways to classify that we'll see in just a moment. Marking tools are ways of coloring the packet so that future routers have an easier time classifying it. Here's what I mean. When a packet comes in, you might pull out an access list. Now, access lists are great for identifying things, but they cost you some time because the router now has to open up and has to look at data in the packet that it might not normally look at. So you're looking at adding a little more delay, and you're looking at adding a little processor load to that router by using the access control list. So what you might do is, look at the data and instead maybe color it and say, you know what, for the future routers down the line, they'll just have to look at the color that I put on this packet and they'll be able to know what it is. The best way I can think of it is think of a shipping company where they put the address label on the inside of the box. Right? You've got this box and it's blank on the outside, and you take it to the post office and say, oh, thank you, sir. And they say, okay, it's time to ship it. Let's cut it open the box and look inside, and you're like, oh, it looks like this is going to Indiana. And you go, okay, put the tag back in the box, close it up, and put it on a truck and go to Indiana. So when it gets to the next stop, maybe halfway there, they go, okay, this blank box, let's open it up. You get my point? So that's kind of what the routers have to do if you're not using marking. So what marking will do is at layer 2 or at layer 3, and I'm going to give you some terms right now. This is considered a class of service marking. This is considered a type of service marking. I'm going to color that packet. Often it will be both, to where I get the IP phone sending a packet. I'm going to say, okay, I'm going to take that packet. I've classified it right here, and I'm going to say it is in the layer 2 header going to have a class of service of 5. Okay, now it's a number. I know I've been saying coloring, but color just sticks better in my head, like it's a red packet, like 5 is red or something like that. Now, when I do that at layer 2, that now gives all of my switches something that they can see, because switches care about the layer 2 information, the layer 2 devices, right? So as it's now passing through my switch infrastructure, this switch is trunked to this switch, to trunk to this switch, come to the core, to all that kind of stuff. As it's passing through there, it's able to, all these switches are able to see that layer 2 devices and prioritize it appropriately. Now, the problem is once you get through the layer 2, the switch network, you're to the router, it doesn't really care much about layer 2, it cares about layer 3. So right next to the IP address information in the packet, I can squeeze in this type of service information. I might say this is the type of service. Again, I'll just throw out 5. And we'll talk about all the different kinds in an upcoming nugget. So now, as you pass this down the way, this router doesn't have to use an access list. He can just look at the layer 3 header and be like, oh, it's a 5. Let's move it on. Oh, it's again the shipping box having the label on the outside, but they don't have to open it up and add delay and processing time to that. They just look at the outside of the box and going, it's going to Indiana. Let's move it on to the next point. So those are your marking tools. Policing and shaping tools. Policing tools are your only, that's the best way to put it, anti-quality of service tools, if you will. It's a way of taking away bandwidth from a certain type of traffic. Come on now. You already know in your network there are things that people do that you want to take away bandwidth from. And I know some of you are like, Facebook, it's like it's gone. What I can do, you could, if you wanted to, set this up in such a way that the internet performs like amazing unless somebody goes to Facebook. And Facebook will be throttled to a let's say a 9600 baud modem speed, like 9.6 kilobits per second. You could do that if you wanted to. So when people go to Facebook, it's like, you're like, yeah, you can go to Facebook if, after 10 minutes the page page loads, congratulations. Although that may not be good because knowing employees are going to sit there and watch every line of the page draw because they have to know that Bob ate tofu for lunch today and posted it to Facebook. So policing allows you to throttle bandwidth back. Shaping allows you to throttle bandwidth back in a kind and gentle way. So the best way to think about that is to say this is traffic that we like. Policing, let's just put the sad face. This is traffic that we don't like. Like, we want to smack this down. It's people surfing the web. It's people using peer-to-peer file sharing. It's people doing stuff on the network that we don't like, and we want to kill it. This is traffic that we like, but we just don't have the bandwidth available. This is typically used for speed mismatches. So let's see. What's the best way to put this? Let's say I've got a connection coming in. Maybe it's a cable modem. Maybe it's DSL. Maybe it's whatever. It's a connection where the line speed of the cable is less than the actual speed that I get. So I come into my router and plug that into a gigabit Ethernet 0/0 on the router. That goes 1,000 megabits per second, but maybe the DSL line only does 4 megabits per second. Well, we've got a huge speed mismatch, and the router, thinking that this is 1,000 meg per second link, is just going to be like pummel, and then, whatever's over here is going to start dropping it, because it's like, I don't know what that is. So what we can do is we can say, I want to apply shaping to this, which informs the router and allows the router to behave that this is a 4 megabit per second link. I'm not trying to smack it down, to where it's like 4 meg and you're dropped. I'm going to try and set this up in such a way that when it reaches 4 megabit per second, it queues. There's the big difference. There's that missing word I was looking for, Queus. Queues the traffic. This, policing, drops the traffic. You try talking and writing at the same time. It's hard. So this drops the traffic. This queues the traffic. So if you go above 4, it's like, okay, I'm going to still put you in memory. I'm going to try my best to send you. Whereas this is like, sorry, bud, you reached your limit. You're done. You're being dropped. So those tools are at your disposal. You have congestion management tools. This is your queuing strategies. And this is what you'll hear most about when you're talking about quality of service. You'll hear things like class-based weighted fair queuing. You'll hear things like low latency queuing, which is how do you handle congestion when it happens? Congestion happens. What do we do then? What traffic goes first? That's the kind of feeling that you get with congestion management. Congestion avoidance, its goal is to keep congestion from happening in the first place. You may have seen before have you ever dragged and dropped a file across the network, a really big file, and you see the copy time, it comes up and it says this file will take 5 days to copy, and you're like, what? And the Windows is like, no, I'm sorry, I meant 1 day to copy. And you shake your head again, you're like, what? And no, you know what I'm talking about. And then it's like, no, how about 23 minutes? And you're like, okay, well, that's better, but what was with the 5 days at first? Well, what happens is TCP windowing is taking effect, where you have a computer that says, okay, well, let's test this connection. I'm going to copy this file, I'll send 1 packet and get an acknowledgement back. Okay, that's great. It got there. Life is good. But it says, but if I have to send 1 packet at a time and wait for an acknowledgement, this is going to take 5 days to copy. So instead, what it does is increase the window size. It's like, let me try sending 8 packets. Oh, that got there, and we get an acknowledgement. And it's like, okay, that's much better. But if I still have to send 8 packets at a time, then I'm going to take 1 day to get there. So what it's doing is increasing the window size. The goal of a computer is to use as much bandwidth as it possibly can. It sounds like a mean goal, but not really. I mean, you want your computers, your data to say, if the bandwidth is there, then by golly, use it. Let's get some efficient transfers out of this. Well, congestion avoidance says, well, you know what? With these TCP window sizes building up, it's not going to take long for one device to start sucking it all up, sucking up all the bandwidth. So what congestion avoidance does is strategically start dropping the traffic. It says, okay, I'm seeing you're building up, and you're going to soon consume all the bandwidth. So before we get to a congested state where the management tools have to come in because we're now full and the bandwidth is gone, before we reach that state, I'm going to start strategically dropping packets to where you'll start shrinking your window size down before we get to a fully congested state. That's congestion avoidance tool. You might hear things like weighted random early detection as one of the tools that you can use. Compression and link fragmentation. This is where you can compress, smush packets down to a smaller size. Or I mentioned this one earlier with RTP header compression, to where instead of smushing it down, you can actually strip data out. Redundant data can be removed and thus making it more efficient. Link fragmentation tools, these are good but not good. On slower speed links, you have something called serialization delay. Yeah, this whiteboard is toast. if you just walked into this video right now and looked at the whiteboard, you won't understand a thing of what's going on. So delay. So that's how long it takes to put a packet onto the actual wire. Well, on really slow links, and what Cisco says is links that are 768 kbps, kilobits per second, or less, is considered one valid for serialization delay. So on really slow links between sites, it takes time to put large packets onto the wire. Well, the problem is when a router starts putting a packet onto the wire, it's too late. Meaning, I just remember this from the top of my head, so let me give you this value. If this is a 56K modem, 56 kilobit per second link, and you try to put a 1500 byte packet onto that line, it takes 214 milliseconds to actually move this packet from the router onto the wire. But the problem is, once the router has committed, I mean, think of it like one of those slow motion movies, where what's that movie? The Rock, where I can't even remember who's it. It's the guy with the English accent. Sean Connery, the guy in the prison, and they've got these balls of poison that can like take out a whole city. It's this toxin gas that they're trying to do, and there's multiple scenes in this movie where in slow motion, like this ball is dropping in, people are like no, trying to grab this ball from hitting the ground, which would like destroy the whole city of New York or whatever the case is. Well, think of it like this: like this 1500 byte packet is a ball of poison that's about to drop on your line, because there's all these voice packets waiting in line, and they weren't there until just a millisecond ago. The router, life is good, we're just sending our packets as normal. It decided to send this data packet down the line, but just as it started saying, okay, I'm going to commit to putting this onto the physical hardware wire, a little voice packet came in and was like, send me, I want to go, I need to go fast, really fast. And so the router's like, no, it's the ball of poison dropping, and the router can't take it back. It hits the ground. Once it commits to sending that large packet, it's doomed. So all of these guys have to wait that 214 milliseconds before this big old packet in front of them gets out of the way. Now you might remember from a couple slides ago, I said your delay goal is one-way end-to-end delay of 150 to 200 milliseconds. Like this packet has to get to the other side and be heard by this phone in 150 to 200 milliseconds. Well, if you've got this big old packet in the way, this 1500 byte data packet, you get the point, right? Before it even leaves the router, it's doomed to a delay life of 214 milliseconds before it even reaches the wire. So it's not good. So what this does is, as packets are coming into the router, all of them that are larger than whatever size you specify get Ginsu knifed. Like, here's your 1500 byte packet. The router's going to go chop, chop, chop. You've seen like on TV where they chop cabbage really fast. That's what it's doing. It's like chop, 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 chop into all these little pieces. So now the data packets are smaller, and it can interleave the voice packets, and they never get stuck behind this big old data packet, right? So that's the goal of link fragmentation. However, keep in mind, this is not a good tool. It's a necessary tool, but the reason we have big packets is it's more efficient overall than sending a bunch of little packets. And what we're doing here is we're taking our big packets and converting them to a bunch of little packets. So it's necessary for voice to work, but overall it impacts your link negatively because you're adding a lot more header information for all these little Jinsu pieces of the packet. All right, last tool. I know, a lot of tools, right, that I'm talking about. These are all tools at your disposal with quality of service. Is bandwidth reservations tools. Specific tool that comes to mind right there is RSVP. That's the technical name for it. That allows you to reserve bandwidth on the line. And that's RSVP can be used to say, I want a guaranteed 20 kilobits per second or 100 kilobits per second on this line. And all the routers in the chain on the way will respond to that and say, absolutely, we will adjust our queues to where nothing can touch that. Bandwidth reservation tools are one of the only ways of getting absolute 100% guaranteed quality of service. Challenge with some of them is they don't scale. I mean, if you have enough calls that say, hey, I want to reserve this bandwidth, you can eat up all the bandwidth and nothing else can use it on the line. So all of these, I mean, big discussion on this tool belt, but those are all the tools we have at our disposal, with all of them geared around one goal in mind, and that is to say, voice packets are more important than data packets. All right, last thing I want to do in this nugget is to give you an overview of how you use those tools. How do you configure those tools on a Cisco device? The beauty is Cisco has made it very simple and very standardized every single time. Set up class maps, policy maps, and what's called service policy interfaces. It's funny, I have to smile when I say this, because learning Cisco is so learning the right way from the beginning. Everybody, I don't know how they get away with this, but everybody out there copies Cisco. You know, I have dealt with Sonic Wall equipment. I've dealt with Foundry Networks. I've dealt with HP. I've dealt with Force 10. I mean, I am done walking into environments where I see a foreign device and I get scared of it. You know, because it's been so many times where I open it up and I get into the command line and I'm like, good grief, this is just a knockoff of what Cisco has, where they change it just enough, I'm guessing, that Cisco doesn't sue them. But I've been on so many different devices that just say, oh, well, Cisco does it that way, so we'll do it that way. And so they use the same exact structure. So total side note, but just keep in mind, this is so the right way to learn it. So class maps. First piece is to define what, as in what do you want to apply some form of quality of service to? Now, you saw all the tools, so you could be saying, well, what do I want to apply policing to? What do I want to apply priority to? What do I want to, all of the tools that we just discussed on the previous slide. This is identifying the what. So think of this as a matching system. That's all the class map is there to do. Matter of fact, when we get into the class map configuration mode, which I'll show you in a split second, you're going to see virtually one command, match. And it's going to say match what? Match, I can say match an access list, match an incoming interface, match a marking on this packet. You can match all kinds of different things. This identifies, this is your, if you want to use a specific quality of service tool, these are all building blocks, by the way, this is classification. This is how you classify your traffic. Now, you get to the policy map, and the policy map is your do. As in, what do you want to do with that traffic? So you've identified that you want to match people going to Facebook.com. Now, what do you want to do with them? And that depends on who you are. You might say, well, I want to prioritize that, or I want my Farmville to perform better. I don't know. But, what do you want to do with Facebook? Do you want to police it down to a certain standard? Do you want to shape it? Do you want to apply low latency queuing and have congestion management? Do you want to do congestion avoidance with weighted random early detection? This is where all your tools exist. So we take our class map, we say, okay, I've identified the traffic, I've classified it. Now I'm going to put that inside. I mean, you literally embed this. So let me get a little more techie on you. You create a class map and I name it. You actually give it a name. This class map is named Facebook. Now I go into my policy map and I say, okay, for the Facebook class, I want to, and then underneath here is where you type your tools. It takes you into a sub-configuration mode of that Facebook class, and I say I want to police it down to 8 kilobits per second, which I think is as low as you can go on the policing. So it applies to that. Now you can keep going. I could say, okay, I want to now create another class, and we'll call it voice. I want to create another class, and we'll call it SQL data. And then under this policy map, think of the policy map. So here's your policy, which we'll name quality of service. That's because you name it. Underneath there, you put in all those classes and what you want to do with them. So we have our Facebook class, we have our voice class, we have our SQL class, and then you go underneath and you say, police this one, prioritize this one, guarantee this one some bandwidth. And we'll talk about some of the tools in depth in the upcoming nuggets, but that's the structure of it. The last piece is where. Where do you want to do that? So you might be on the router and say, well, okay, here the T1 will say interface serial 0/0 over here. That's the where. So I'll take that quality of service policy and I will apply it to that interface. So I'll say this structure, these tools will apply as the traffic decides to go out this interface, maybe towards the internet connection. That's the where, and the way that you apply it is a command that's called service service dash policy. Let me do this. Service dash policy, and then you apply the policy. So I haven't planned on doing this, but let me do an on the fly demonstration. Let me just make sure I have a router ready. Okay, I do. Why would I not have a router ready? Doesn't everybody have a router standing by? So let's just go with a Facebook thing. Let's again, this is this is non-scripted, so we'll see how it goes. So let's just say, I'm just gonna again keep in mind this is just an example. Let's just ping facebook.com. Okay, and I say, okay, facebook.com comes from this IP address. Now, keep in mind, Facebook is big. They're going to have multiple IP addresses. They'll be on multiple data centers. So you would have to go somewhere online and find out all of the IP addresses that facebook.com might use. But here's what we would do. I go IP access list, extended. So I'm going to, now, and you could do a numbered one if you want, but I'm going to name this guy Facebook ACL. So I'm in the access list, and I'm going to say permit. I'm going to essentially match. I'm going to say I want to catch any, or let's do IP, any source going to the destination of, let's just make it simple, 69.171.234.21. I want to catch any source going to this destination. That's it. With any traffic, HTTP, FTP, whatever. I'm catching it all. Okay. Good. So that's kind of like an identification system for Facebook. Now we get into this three-tiered structure. First off, the class map. What do I want to match? I'm going to say class map, and you can say we've got this name. Now notice it gives us the option of match all or match any. So I can have multiple criteria under there. For instance, I keep losing my pen. There we go. So let's say I have a class map Facebook, and I say I want to match the ACL Facebook that I just created. I want to match the input interface fast Ethernet 0/0, like it came in on that interface. I want to match the type of service, the tag on the header of 5. So I can actually put all of these little attributes underneath there. So if I say match all, then all of these have to be true. So if it's going to Facebook, it came in this interface, and it has this tag, then it matches. If I choose any, then any of these would be true. Like if it came in and it's going to Facebook, it'll match. If it came in this interface, it'll match. If it came in with this tag, it'll match. So that's probably not what we would want in this case, and that's why the default, if you don't choose anything, if you just name the access list, or the class map, it's going to be match all. So I'll type it in just for grins. So I'll say class map match all, and we'll name this Facebook CM. You see why I'm doing this is so I can distinguish which one's the ACL, which one's the class map, and all that. So I'm going to say, okay, now that I'm under here, let's hit the question mark. Remember I said pretty much the only command you have is match. That's the truth. So I'm going to say match, hit the question mark. Now it's saying, okay, well, here's the stuff I was just reviewing in the upper right corner there. Do you want to match an access list, which is in there? Do you want to match any traffic? Do you want to match another class map? You can actually, this gets crazy, embed class maps within each other to where I say, well, I want to match Facebook, but now I want to combine it with something else. Do you want to match a certain class of service? That's the layer 2 tag. You can just browse through this list. You see, it's very flexible in there. In our case, I'm going to say I want to match an access group, which is going to an ACL. So I'll scroll back up and say I want to match that guy. Oh, wait a second. It's probably going to ask me to type in the name. I knew it. It's not all capital, so I have to type in name and then paste it in there. There we go. Facebook ACL. Okay, so I've done step 1. I've said, here's what I want to classify. Okay, step 2, policy map. I'm going to say policy map. Let's do Facebook Smackdown. That's the name of my policy. So I'm going to say that the policy map is Facebook Smackdown, and you can see now underneath here, nothing to it. It's just saying, okay, how about you say what class this applies to? Remember I said all of policy map is, yeah. So I put my pen on the top of my desk, and it rolls and it falls off into the great abyss of my desk, which literally, it's this messy, I can't find, hang on. Okay, I got it. So the policy map is really just a series of classes, and what do you want to do to each one of them. Now, we only have one class at this point. That's what we're creating. So I'm going to say the class is going to be Facebook underscore CM. You see how kind of it's like Lego pieces. You're snapping them all together. We created the Facebook ACL, which match Facebook. We said, here's the IP address. I came down and I said, okay, the Facebook class map is going to match the Facebook ACL. So it's kind of like they build on each other. So the class map is going to say, match this guy. And now the policy map is going to say, okay, for the Facebook class map, enter. Notice now the mode we're in. We're saying, okay, what do you want to do to that specific class of traffic? And that's where you see all the tools that we talked about on the previous slide. You know, this is where it all comes together, to where it's like, okay, do you want to prioritize them? Do you want to guarantee them a certain amount? Do you want to compress them? Do you want to drop them? Ooh, that's good. Do you want to, use shaping tools? I mean, everything that we talked about just a moment ago. In this case, I said I want to police them. I want to police Facebook.com down to 8,000 bits per second, which is 8 kilobits per second. So now I've really limited. Now I can just leave it there, but you notice I can even be flexible. I can add a little buffer. I can say, okay, if it conforms, then allow it. If it exceeds, then maybe we can be a little gentler. We can say, well, maybe allow it, but tag it a different way so that it doesn't get quite the priority as normal. Different scenarios that we could do. And if it violates. Now violate. So this gets into traffic shaping, which is not part of what we talk about in CVOICE. It's really more of an advanced quality of service topic. But here, I'll give you the flyby overview. You're gonna love it. It's really not too bad. Think of it this way: when your router is sending traffic, the router is kind of keeping track of it and banking it. So let's say I define a committed information rate. Like, this is the normal rate I want to send at of 8 kilobits per second, right? This is our Facebook. And let's say, and here's time. So as we have time going on, you can actually have it say, okay, well, Facebook.com didn't use anything for that first time interval. And you can define how long that time interval is. And then all of a sudden they went up and they consumed a little, and then they came back down. Let me just draw this dotted line right here. They came back down, and then they went up right here and came back down. And then all of a sudden they went up and needed a little more traffic and went above the CIR. Now, what's that mean? Okay, this is, if we go back to the actions, this is the conform. It's where, okay, you are conforming. You're staying below 8 kilobits per second. This is exceeding. I say, well, what's that mean? That means the router looked at how much bandwidth you were using, and it said, you know what? You're not using. This is like banked bandwidth. You're in your bandwidth bank right here. Like, you saved a few pennies in your bank right here. So when you needed a little more than what I'm typically giving you, I'm going to allow you to exceed, but only up to the level of your bank account, how much bandwidth you've banked. Now it's not like, overnight, you don't use Facebook at all because everybody's asleep, and like you come in the next morning, it's like, we've banked tons of bandwidth. There's a cap to the bank account that is set, but once you reach that cap, now you've got this bank balance, so you can go in this exceed territory. Now, what happens when your bank account balance runs out? You, my friend, are in terms of violation. That's that third action down here. You are in violate mode, to where you're now, you're no longer considered bursting. You've exceeded your bank account. You're living on credit, the American way, right? You're living on credit. So now what do you want to do? So you can define different action. You can say, okay, if it conforms, go ahead and send it. If it exceeds, sure, go ahead and send it. It's using some banked balance. It's being responsible. But if it violates that, no, I'm sorry, you're dropped. There's no allowing that to go through. So that's the idea of this. So when we come back here, let me exit back out. How many levels are we in here? Show policy map. right here is how it's doing. It's saying, okay, we've got policy map, Facebook Smackdown. First class that we have in there is Facebook class map. We are policing it. And we filled in 8,000 bits per second. It went ahead and automatically said, okay, that means that's your committed information rate. This is your committed burst. You got a little 1,500 byte committed burst. Conform, transmit, exceed, drop. That's the default. We didn't actually type that in. So now, that would be our first class that's underneath here. Now I can go through and continue adding more classes if I had them created. But then, the last piece, as I apply it. So let's say I want to go into fast Ethernet 0/0 and do a service policy. Now it says what direction. I'm going to say, well, as it goes out or as it comes in, depending on what tool and what direction I'm using. As it goes out this interface, I want to apply the Facebook Smackdown policy. Enter. Now it's taking effect. Now I'm throttling traffic to that IP address down to 8 kilobits per second. So again, an on-the-fly demonstration, but that's it. I mean, that's the beauty is every tool that you use with quality of service is going to be applied using this three-tiered system. What do you want to match? What do you want to do with it? And where do you want to do it? Well, you ready to make some sugar cookie? Just make sure you add that cup of sugar of quality of service. What do we see here? And what do I want you to do with it? We have seen the evil villains. We saw the lack of bandwidth, delay, packet loss, and jitter. Those four, think of it, the evil four that we are fighting with our quality of service. And we saw all the tools, the congestion management tools, the congestion avoidance tools, policing, shaping, that whole category of tools. And then we saw the modular QoS CLI, class map, policy map, service policy, commands that we use to apply quality of service every time. Now, this has been a thick nugget. I mean, it's like just dense with information. So what I would encourage you to do right now, before you go on to the next one, is review it. Sure, you could go back and rewind and play it again, but then my jokes probably wouldn't be as funny or anything like that. What I mean by review it is kind of scroll around in there, get to the slides, get to one. When you look at the tools of quality of service, congestion management, policing, shaping, all that, and I want you to write them down on a piece of paper, like spell them all out, and then go online on Google, or even better, go onto your router and get into that policy map configuration mode where remember where I hit the question mark, I said, here's all the tools, and see if you can categorize what tools go under which categories. Because that's really, I mean, think of this, it's like, continuing the superhero analogy, if these are the evil villains of quality of service, you are flying this spaceship that has all the weaponry necessary to take out these evil villains. However, you got to know what the buttons do. You can't just push a button and expect it to destroy delay or anything like that. You have to understand what buttons you have at your disposal. So take that list and start going through it and chalking it up. Also, especially if you have a router, start configuring a few policy maps. Create maybe 5 different classes of traffic. Be creative. Identify web traffic, FTP traffic, some voice traffic. Find different ways to classify them. Create 5 separate class maps, and then assemble them all into one big policy that does different things. Now, at this point, we haven't gotten into what we can do with that policy map, but I'll tell you, you can start exploring and using the question mark, becoming really familiar with what some of those tools are able to do. Then jump into the next nugget where we're going to kind of dissect the tools one by one. I hope this has been informative for you, and I'd like to thank you for viewing.